Hi, cool coders. Welcome to Cool Enough to Code. This week we'll be looking at basic mathematical operators like addition, subtraction, multiplication, and division, and some other ones related to these that we will be using a lot in our code. So last week we looked at variables and data types. So we're specifically going to be looking at numeric data as we do these kind of operations on that data. And this is where things get a little bit more interesting when we start to combine things together using mathematical operators rather than doing strings like we did with concatenations in our last exercises. So let's go right over to the deck and take a look at what you can do with mathematical operations inside of Python. So let's do a quick review of what we talked about last week. We talked about different kinds of data types. We talked about Boolean data and string data. And we also talked about numeric data, which is what we're going to be talking about today. And we talked about integer data, which is data that is numeric without a decimal. And we talked about floating point data, which is numeric data with a decimal. And we made the distinction here because it's important to know this, because when we're talking about computations on this data, integer data is generally going to be much faster because the circuitry on a computer to handle this is simpler and much faster than floating point data. So we have two different data types to represent that. We also talked about variables and how you can use these to store values in RAM and then use a program to change it. And you can also change the data type whenever we're talking about variables. And there were some examples that we gave right there talking about numeric data and string data. Now we're primarily going to be focused on variables for numeric data this week. Last week we looked at string data and we looked at how you can use variables with string data. And we talked about casting and types. And remember, casting is the ability to convert between one data type to another. And sometimes you might end up losing data on that conversion, such as going from a floating point number to an integer. And we also talked about the type function, which shows you the kind of data that you're dealing with in a particular variable. So that's a brief recap of what we talked about last week. Let's go into the new content, but I want you to kind of keep this stuff in the back of your mind because we're going to be using it as well in this week's lesson when we talk about doing casting from input that we take into other kinds of data type, and that will become important, especially when we're using the input function. So let's dive right in and talk about mathematical operators. Now, Python, of course, has the basic ones available right out of the box for you in the language for doing basic mathematical operations. You have addition, which you would expect to use a plus sign, so x equals 2 plus 1. That's very straightforward. And with subtraction, very much the same. You can access that on the keyboard with the minus key, and then you can do x equals 2 minus 1. And then multiplication, other than using an x, it uses an asterisk instead. It's pretty much the same as you would do it if you were writing. So 2 times 2, and I use an asterisk and I would get 4 naturally in that case. Something to remember when you're doing basic mathematical operations in a computer is that if you're mixing data types, it's going to go up to the more complex data types. So with integer math, we're going to be adding integers together. So 1 plus 2 is going to return an integer. But if I was adding 1 plus 2.1, I would have to first do some casting in order to do that operation because I'm adding an integer to a float. Now Python's going to automatically do that for you, so you don't have to explicitly cast an integer to a float if you're mixing different kinds of numeric data, but it will return a float if you do that. So it's important to remember that it will do that cast for you. So if you're expecting something like a float in return, then make sure that you're putting in floats for your different kinds of numbers that you're going to be adding, subtracting, or multiplying together. Now, I haven't mentioned division, and that's because division is a little bit tricky in a computer, and there really are 3 different operators for division. But let's go to the IDE and look at these first 3 fairly straightforward ones first, and then we'll come back to division and look at that as more of a special case because I want you to see it more up close because it does have some idiosyncrasies about it that will take some getting used to if you're not used to doing division on a computer. Okay, I'm here in Tony, and the first thing I'm going to do when I do mathematical operations is put a comment down. And commenting your code is always good so that you can let the people reading your code knowing what you're doing in something that's other than the code itself. So before I do anything, I'm putting a comment down. It's a good habit to get into early in your programming career, is commenting your code. So I'm going to do that first just to set a good example here. And then I'm going to actually do a variable assignment. So this x equals 1 plus 2. And then I'm going to print the results of that. And I'm going to then print the type as well. And I'm going to do this to show you that I'm doing integer arithmetic And then just to validate that I am indeed using integers. Let's change the operator to subtraction, and one more time for multiplication. So let's do that. Now let's run this, and we will get a result: 3 integer, -1 integer, 2 integer, and let's run that, and voila, that's exactly what we expected. So let's do the same exact thing for floating point now, except I'm going to convert some of these numbers, and first change this to floating point, and let's do 1.1 and 2.2. Let's do 1.0 and 1.2.2, and then let's change this value down here to 2.1, and let's do this one to 2.1. Now, when we add these together and subtract these, we might expect these to be nice, neat, round numbers. We expect this to be, for instance, 3.3, but let's run this and see what we get. And there we go. Now you're wondering, why in the world am I not getting some nice, neat, rounded numbers here with 3.3 or 1.2 is which we would expect. And this is getting into the weeds on the way that a CPU handles floating point. Remember, like I said, that floating point math on a CPU is done with specialized circuitry, and that specialized circuitry is designed to first take some numbers that are decimals. That's what the computer is going to do, is going to take these numbers and convert them into a binary representation. So it's going to convert 1.1 into a binary number and 2.2 into a binary number, and it's also got to represent the decimal in that as well. Part of that conversion process inevitably is going to result in some small rounding issues, and so what you end up with inside of the CPU is an imperfect representation of what is perfectly represented in decimal right here. That imperfect representation is a binary representation so that the computer can actually do the actual work on that number on the CPU as binary, and then it's got to convert it back into the decimal form that we have displayed here. And as a result, we get a small rounding result that results in this long sequence of zeros with this 3 at the end of it. And the same thing here, we end up with a long sequence of zeros with a 2 at the end of it. Some people, when they first see this as a new developer, they think, oh, it's a bug. It's not. It's just the way that floating point exists inside of a computer, and this has been a problem inside of computing since the inception of the computer. This is an issue that has to be dealt with when you're coding. So not a big deal for precision for a lot of different applications. Again, that's 3 quadrillions or whatever. I don't even know. I didn't count those number of zeros, but it's a very small rounding. It's not going to affect a lot of the results that you're trying to deal with, but sometimes the results can be a little bit anomalous if you're trying to do something and you end up with something like 3.99999999999 or something like that, wherein you've got a small rounding issue there as well. And it's always important to try and figure out what you're dealing with here, or make sure that you have rounding going on inside of your code. And there's ways to handle that. We'll look at that in just a moment, so that you can handle these kinds of anomalies. They're not really anomalies, it's just the way that floating point is handled on a computer. This one came back nicely, and that's because the computer was able to represent both 2.1 and 2.1, obviously same number, more perfectly inside of binary than it would be able to represent these other numbers in binary as well. So something to keep in the back of your mind. I'm making a big deal about this because I want you to be aware of it whenever you go to write your code and you start to see these results. It's not a bug, it's just the way that floating point inside of a computer is handled. So let's go ahead and take this same code and let's mix some results here between integer and floating point math, just to show you that it is going to convert things to floating point. Because if I'm dealing with something like an integer, I can't exactly add an integer to a floating point and get back an integer. I need to first convert this to floating point. So let's just change this to floating point number into an integer, and let's do the same down here, so that I have an integer in each one of my operations, floating point mixed with integer math. And similarly, we should expect to get back a bunch of floating point numbers as well. Notice this one, we did get back 3.2 nice and clean like we would expect, and that's because this number is the one that's more represented perfectly inside of binary. And this one down here, similar result. We got something that was more imperfectly represented in binary by the conversion, probably this number right here, and then the actual arithmetic that was done on that returned back a rounding issue as well. But down here, same thing. We got back 4.2, which is exactly what we'd expect, but all of those are floats. So we want to be able to be aware of that whenever we're doing integer and floating point mixing inside of our computations here. So something to keep in mind that it's going to convert integers into floating point if you're mixing floating point with integer math. So let's go back to the deck and look at division now, which is also going to have some idiosyncrasies about it that you need to be aware of when you do these. So let's look at division now. Now, division has three cases. The first one is integer division. Now, look at this particular example that I have here. I have 5 with 2 forward slashes and 2, and it gives me back a 2. 5 in this case is a integer, and 2 in this case is an integer. But when I divide the integer 5 by the integer 2, I get back some result that is not an integer. I get back some kind of number that has a decimal part to it. And in this case, with division, I can divide something by another entity and get back something that is not like the two numbers that I am putting into the operation, like I did with addition and subtraction. So with addition, if I add two integers together, I'm always going to get back an integer. If I subtract two integers, I'm always going to get back another integer. If I multiply two integers, I'm always going to get back an integer. With division, that's not the case. I can divide one integer by another and get back something with a decimal, which in that case would be a float. That's why I need the special operators to declare my intent here. I can't infer that intent based on the kinds of inputs that I have into the operation that I'm trying to perform, like what we saw whenever we were doing integer math already. So in this case, I'm saying I want an integer back. And this case, I'm doing 2 slashes, and that says, give me back the integer portion of this operation, which in this case is going to be 2. So basically it's doing 5 divided by 2. It's getting back 2.5. It's dropping the decimal portion and returning the integer part of that number. It's basically going to do what we call a floor, or it's going to shift to the left on the number line. If I was to do this in negative numbers, say I had -5 divided by 2, I would actually get back 3 because it's shifting to a lower number on the number line. If I do it in positive numbers like I have here, 5 divided by 2, I'm going to get back 2. So that can be a little bit confusing for folks, but it basically is just shifting to a lower number on the number line, and -3 is lower than -2. So that's something to keep in mind whenever you're doing division, integer division, particularly with Python or any other language for that matter. Now, the next one is floating point, which is represented by a single forward slash, so 5 divided by 2. In this case, I have 2 decimals that I'm going, a single decimal that I'm going to be getting back with this operation. I have 2 integers dividing one integer into another, and I get back 2.5. So that is a floating point number, and it's floating point division, and that's exactly what I would expect. This is one of the most commonly used operations for division because people want that decimal represented, so they will use floating point division even though they're dealing with integers, and that is going to result in some kind of result that you would expect here, 2.5. And there is another division operation that is available inside of Python or any language called modulus. Now, if you go back to the days when you were learning how to do long division or division in general in grade school, like 4th or 5th grade, you got used to doing long division, and you would sometimes have a remainder left over, and that remainder was some fraction that was no longer divisible beyond whatever it is you're trying to get to. So maybe you're trying to go to 2 decimal places, you have some kind of remainder at the end of that number, and you just put R and then the number that is left over. Modulus is essentially that. It's the remainder portion of a division operation. So if I go 5 mod 2 or 5 modulus 2, I'm going to get back a remainder of 1. If I do 4 mod 2, I would get a remainder of 0 because that divides into it evenly. And so this is how you can get back that remainder portion of the division operation if you're wanting that kind of division to go on. So I could use integer division, say 5 divided by 2, I get back 2, and then I do a modulus division and do 5 modulus 2 and get back 2 remainder 1, which is again a representation of the same kind of thing that I would get if I was doing the decimal division with the standard floating point division, which is, you know, effectively 2.5 in that case. So let's go over to the IDE and look at division inside of Python, and let's look at some of these results so that we can get some visual representation of what we're talking about here, because this is again one of those kind of confusing things that if you're not used to it, it can be a little bit hard to grasp at first, but once you get the hang of it, it's really not so bad. Okay, I'm here in Tony, and let's do a little bit of division here. Let's start off with a comment, of course, integer division. And see if I can spell it right. Yep, there it is. And let's do x equals 5 divided by 2. And let's print out x. And let's also print the type for x, just so I can validate that I'm actually dealing with an int here. And I also want to put in the results for negative 5 divided by 2, and I want to show you these differing results. Remember, I said that this will do a left shift on a number line. So down here we have 2 for our first operation and negative 3 for our second operation. So let's put a little number line here on the screen: negative 2, negative 1, 0, 1, 2, and 3. So if I do this operation here, I'm getting a result that's between 2 and 3. So what it's doing is dropping the decimal portion and going to the left on the number line to a lower number, in this case 2. Same thing's going on here. It's actually taking negative 5 divided by 2. It's getting a result between negative 3 and negative 2. It's dropping the decimal and going to a result that is lower or to the left on the number line, which in this case is negative 3. And for somebody that is trying to look at this, it might not seem intuitive, but it's actually doing the exact same thing if you look at it from the perspective of a number line. And that's exactly what is going on here. So let's look at one other result here that I want to show you. And this one, it might be not what one might expect as well. That's if I use floating point numbers inside of an integer division operation. So in this case, I'm still going to get back an integer result, but it's going to do a cast to a float because I'm putting in floats into the operation. So notice I get back 2.0, and the result is actually a float. And that's because even though this is doing integer division, I am getting back a float because my inputs were float. And that's what Python is converting this to. So again, it still came back as an integer, but because of the casting and the inputs, it's doing a casting back to a float for that reason. So that might be a little bit of of idiosyncrasy about this if you weren't expecting that, but it's still fundamentally doing integer division, even though my results are coming back as a floating point number. And under the hood, it's actually doing integer division. So let's do some floating point division now. So let's get a comment here called floating point division. And let's fix my spelling error there. And let's take this same code here and paste it down here. And let's change all of these results here. And I want to add one more operation here. And this one, I'm going to take this one and do 4 divided by 2. Now let's run this and we'll just get a bunch of numbers back. And in this case, I'm getting back all floating point numbers. So notice what I have here: 5 divided by 2 is exactly as we expect, 2.5. Negative 5 divided by 2 is going to negative 2.5. Floating point divided by floating point, again, yet floating point. And in this case, I have two integers using floating point number division, and it's also returning a float. So unlike the integer division that we saw up top, where we had two floating points, but we used integer division and got back a floating point number. In this case, I'm using floating point division with two integers here, and I'm getting back a floating point. So that is something that's a little bit different if you're doing floating point division rather than dividing two floating point numbers using integer division. I know this terminology can get a little bit mixed up if you're not used to it, but the point is that in this case, even though I'm passing in two integers, I'm using floating point division, I'm getting back a floating point number, while up here I'm using integer division, passing in two floating point numbers and getting back a floating point number. So something to mix up real good there with the terminology, but I think when you see the symbols and the results, it's actually a little bit more clear than trying to explain it. Now, the last thing I want to look at is the modulus, which is something like we said, it's the so-called remainder that we had when we were doing long division inside of our grade school grammar or grade school arithmetic books, that where we had what is the remainder of x, y, or x divided by y. And with this, we're essentially getting that same result. So let's do some of this right here. So let's do x equals 5 mod 2, and we should get back 1. And let's also do I print and the type for that, just so that we can validate that we're getting back something that we expect. And let's do 4 mod 2, and then down here I want to do some integer division using modulus as well. So 5 divided by 2.4, something like that. And that's a modulus function as well. But for this operation here, let's go ahead and run this, and let's see what we get. So here we got back the expected result. We're getting 5 mod 2. The remainder of that is 1. So 2 will go into 5 2 times, and you have 1 left over. That's my so-called remainder, or my modulus in that case. And the case here, again, 2 goes into 4 evenly. I have 2 with no remainder, so we get back an integer in that case. Now down here I did some floating point math, and this is what we'd expect here. So this will give me the similar result. This is actually to be expected here. This will go into that twice with a remainder of 0.2 because this will be 4.8, and then you would, if you're doing long division, you would subtract that, and then you would get back a remainder, if you will, of 0.2. And it's the same result that we would expect. It's not clearly that remainder portion, but the idea is this similar. But because of the rounding issues that we end up with floating point arithmetic inside of a CPU, we have this rounding issue right here that we have to contend with as well. So again, that rounding issue is going to pop up every now and then. It's not a bug, it's just the rounding error that happens whenever you convert numbers into binary. You do arithmetic on them, and then you convert them back into decimal. Inevitably, in that conversion process, there is almost always going to be some kind of rounding issues that you have to contend with. So you just have to make your program be able to handle that, and we'll look at a way to do that in just a moment. For our next topic, I want to look at some more mathematical operations in the context of parentheses. So if you go back to your grade school math or your junior high school math, you remember, please excuse my dear Aunt Sally, or PEMDAS, for orders of operation. Now, this is also supported in most programming language, and Python is certainly no exception. So you would have, some kind of parentheses that you can put around mathematical operations, and then things inside of parentheses will be evaluated first before the things outside the parentheses get evaluated. So a couple of examples here. We have 2 plus 3 times 3 plus 3, and that would of course be 6 times 9, which would evaluate to 54. Then on our second one, we have a parenthesis embedded in a parenthesis, so we have 3 plus 2 plus 3 minus 2 times 2. So again, the inner parentheses get evaluated first, then the outer parentheses get evaluated next, and then all of that gets multiplied times 2. So let's go over to Tony and take a look at parentheses in the context of mathematical operations as well. Okay, let's first start with a comment here in Tony, and I'm going to start with no parenthesis because I want to modify what I calculate with no parenthesis by adding parenthesis to it. So let's do x equals 5 plus 5 times 6 plus 4. So in this case, I'm going to be doing multiplication first. So it's going to multiply these two together. It's going to give me 30, and then I'm going to add 5 to that, 35, and then I'm going to add 4 to that, so I should get 39. So print x, and I should expect 39 as the output. So let's go ahead and run that just to validate it, and everything is as expected. So let's add some parentheses to this. Let's comment the code as well with parentheses, and I'm going to put parentheses around this first term and the second term, and let's put it around this one right here. So in this case, because of the orders of operation, I'm going to do what's inside the parenthesis first. So 5 plus 5 is 10, 6 plus 4 is 10, and then I'm going to multiply those together. So 10 times 10 is 100. So let's run that and see what we get. So again, 39 and 100, just as we expected. So again, you can see how using parentheses can change the order of operations for your calculations. Very useful for calculating things that need to have a specific order done. So just like math, the languages that use parentheses will support this, and Python is certainly no exception in this case. So now I want to talk about rounding numbers. Now, a minute ago, I mentioned that this is how we can solve the problem where we might have a long sequence of nines or a long sequence of zeros for what might seemingly be an error in Python, but it really has to do with rounding issues at the binary whenever I'm trying to represent a specific decimal number inside of binary. So the way this is done in Python is with the round function, and the round function has two parameters: what value you want to round and the precision that you want to round to. So some examples of this might be as follows, where I have round, where I have 2.5 times 2.51. Well, we would expect that particular operation to have a precision of 3 decimals after it, because I have in my multiplication there, I have the 3 numbers after the decimal, and that's what will determine how many decimals. But I want to round that, so I'm going to say round that to 1 decimal place. So that is the last parameter that I have inside of my round function here, and I would get back 6.3 in that case. And to handle that kind of behavior that I talked about a moment ago, where I have a long sequence of zeros or a long sequence of nines, I can also use round to handle that. So in the case where I'm adding 1.1 to 3.7, I'm going to get some value that's going to be like 4.8 and then a long sequence of zeros and something after that. Well, I want to get a specific precision about that. So I'm basically going to tell Python, hey, round this to 1 decimal of precision for this particular calculation. So it's going to do exactly that. And it's basically going to see that second decimal place as a 0, and then it's going to round up or down, but it's going to be a 0. So it's naturally going to round down to 8. So I'm going to get back 4.8, and that's really the value I want, but the actual floating point calculation is going to return something radically different than that, which is because it actually is doing rounding when it's doing that binary conversion that we talked about earlier. So let's go over to the IDE and look at Tony and look at an example of this and how you can use round to kind of fix some of those issues that we've seen with the conversion into binary and back into decimal. Okay, let's look at rounding now here in Python. So let's start off with a comment, rounding, and let's just do a number. X equals 1.3, well, 1 divided by 3, 1.32. And let's do print round, and let's just pass in X. And that is going to round to the nearest integer part because I don't have any decimals specified in that. And then again, if I do round x comma 1, I'm telling it I want 1 precision of decimal in the round. So I would expect this to put out 1 and then 1.3. So let's go ahead and run this and see what it does. And that's exactly what we get right there. So that's pretty uncontroversial. Now, there are some idiosyncrasies about rounding in Python when it comes to rounding at the halfway point, rounding 0.5s. And this is something that can be perceived as a bug, but it really gets down into the weeds of the way that rounding is handled inside of Python. So let's go ahead and round 1.5 and then round 2.5. And this will kind of illustrate what I'm talking about. In one case, what I'm going to end up with is something rounding up, and then one case, something rounding down. And for some folks, this might be a little bit confusing for them as they go forward. And I'm not going to get down into the weeds about why this is the case, but sometimes 5 or halfway between two numbers will go up, and sometimes it will go down, and it really gets down into the binary representation of these numbers and how one will go one way and one will go the other way. But sometimes this can be perceived as a bug inside of the rounding issues that are going on inside of Python, but it's just something to be aware of, that sometimes round will send something up like it did here. It rounded up to 2, and then right here it rounded down to 2, even though they both end on 5. And I'm not, like I said, I'm not going to get into the details of that, but just understand that's one of the idiosyncrasies of using Python round function when you're ending in 5. However, otherwise it's going to behave as expected. Whenever I have something that's less than 5, it's going to go down, or something greater than 5, it's going to go up. Now let's look at the rounding function whenever it comes to different kinds of precisions as well, whenever I'm dealing with some of those issues where I have a long sequence of zeros or a long sequence of nines. And the example that I gave earlier where I had x equals z equals, that's fine, 1.1 plus 3.7, and I was going to get back, I should expect to get back 4.8. However, because of the rounding in binary, not using the round function, it's just doing that rounding issue that I have when I do a conversion of decimals into floating point in binary, I get some rounding issues. So that's going to print out some kind of idiosyncrasy that is going to be 4.8, long sequence of zeros, and then a 1. So this is one of those cases where I can use round to handle some of that if I want to. So in this case, I really only want 1 precision of decimals, so let's just assume that's what I want. And so I can do a round on z, and I'm going to say 1 precision of decimal. And in this case, this will print exactly what I want, which should only be the first decimal place rounded down. So in this case, 4.8, and it's basically saying 0 right there. Okay, it's 0. I'm going to round down, and that way I'm going to 4.8. So this is how you can handle some of those idiosyncrasies inside of your applications if you're getting these rounding issues when the conversion is going to a binary number, but I only need 1 precision or 2 decimals of precision, and I can say round that. So it's a good thing to have the rounding function available to you inside of Python to prevent your application from having some unexpected issues. I can tell you one application I wrote that was dealing with mathematical functions that were dealing with rounding issues, and it was dealing with financial data, and it would sometimes result in a calculation that was 1 penny off from an expected value. And that's because of a rounding issue using floating point numbers like this, and it would result in just a smidge of a penny off in the final result. And people were like, why is that happening? And I had to explain it to them, and I had to go back and write a bunch of code to kind of handle those cases where I was ending up with these kind of rounding issues out here in this umpteenth decimal place way out here. So something to think about. In some cases that doesn't matter, in some cases it does. So it's a matter of what you need your program to do and how your program is expected to behave. In financial calculations, a penny can be a big deal. In some cases it's not a big deal, but it's just something to consider when you're dealing with money and you're dealing with conversion currencies that have multiple decimal places, etc. But in any case, have a knowledge of it and know that it's there for the purpose of rounding. The last operator I want to look at today before we go to the challenge is the exponents operator. And this is a fairly straightforward one. You simply represent it by 2 asterisks, so star, star, and you can use it just like the multiplication operator, except you just put 2 stars in there. And an example would be the example I have here where I want to get the square of 5. So I would do 5 star star 2, and that would square 5, so that would give me 25 as the result. And if I want to get a square root as well, I can do that fairly easily by just taking something like 9 star star 0.5, because 0.5 is actually 1/2 or 1/2. If I take a number and I raise it to the 1/2 power, that is exactly the same thing as doing a square root of something. So I can effectively get a square root by taking 9 and then doing a power of 0.5, and that will return 3. Let's go over to Tony, the IDE, and take a look at some examples of this. This is fairly straightforward, so I won't spend a lot of time on it, but it's something that's very powerful in Python without having to add some additional functionality to Python. Now I'm back here in Tony. Let's do a little bit of exponential math here. Let's first start with a comment, exponents. And then let's do x equals, let's do a square first, and let's do 5 star 2, and let's print x here, and let's get the result back. And I'm getting 25, so that's 5 to the second power, or 5 squared. If I wanted to do a square root of 5, or rather a square root of some number that is a perfect square. Let's do 9, and let's do it to the 1/2 power, or really the square root. I should expect to get back 3 in that case. And so I'm actually getting a floating point number back there because I have a floating point number here. But you can see here that I am getting back the square root of 9, which is actually the 9 raised to the 1/2, which again is a square root. So doing exactly what we would expect it to, using exponents and the exponential operator with 2 stars. And before we go to the challenge, I do want to talk about one last thing, and that is numeric input. And this is more of a reminder, so we're not going to do a demo on it, but basically how to do numeric input. Remember that whenever we do input from the input function, we get that back as a string. So if we wanted to get numeric input, we need to do some kind of cast to that particular data type that we want. So in the case of floats, it might look like this, or an int, we would put an int instead of float, but you'd basically say x equals float, and then open the parenthesis, do an input, and then ask for some kind of value. So input a floating point number, and then close up those parentheses at the end. And this will give me back a floating point number. Now, if somebody goes to put in bad data, you're going to get a problem in your program, and we'll figure out how to handle that in future lessons. But for now, just assume that your users are going to be putting in good data and that you will be able to handle that by a simple cast. So let's just go with this for today. But let's go over to the challenge and take a look at that now. So for the challenge this week, I want to do something that's kind of a fun equation that is fun to solve, and it's something that is kind of a thought-provoking equation, and it's called the Drake equation. Now, the Drake equation was something that was proposed by a guy named Frank Drake back in the 1960s to do a thought experiment as to the number of communicating technologically advanced civilizations there are in our galaxy. And based on some assumptions, you could come up with a number that would be a representation of the number of potential civilizations that we could communicate with from Earth that exist in our galaxy. Now, again, there's no validation of that any of these values are true, but it's just a fun thing to play with so that you can think through possibilities and different assumptions about that. So let's take a look at the values first, but let's talk about what I want you to do in this challenge. I want you to prompt the user for each of the values in the equation, and then you take these by way of an input, and then you would cast them to the appropriate data type, and then you would perform a calculation using all the variables from the equation, and then you would basically print the result back to the screen. So let's go look at the Drake equation and what that looks like, and so you have an idea what those values are. So let's talk about the Drake equation for a minute. As I said, this was developed as a thought experiment to estimate the number of technologically advanced communicating civilizations in our galaxy currently that we could potentially communicate with. And depending on what values you put into this equation will determine the value for D, which can vary widely depending on the assumptions that you make. Again, we don't really know definitively what some of these values are, so the estimates can range literally from thousands of potential civilizations like we would see in Star Trek to maybe only a single civilization, our own, that we know of. And the values for this, again, are all assumptions. It's just getting people to think about what might be out there that we are currently trying to discover by way of telescopes, ground-based and space-based telescopes. So let's go into the values and look at what these might be. So the value for R is the number of stars that form in our galaxy each year. Based on observational science, we are able to determine this to be between 1 and 3, and that's a safe assumption. So you can put in 1, 2, or 3 for this value. Now, the next value is the number of stars that have planets around them. Again, based on observational data, we know this value to be around 0.5. So that is because in space we have space-based telescopes, and on the ground we are detecting that about half of the stars that we are observing have planets around them. Now, the next value is E, and that is the number of planets in a given solar system that could support life. That doesn't mean they do support life. In our solar system, we know at least one that does, and that's the one we're on, Earth. Now, it is potential that we have another one that is available to support life, and that is Mars. Some argue that it can't, some argue that it can, some say that potentially in the past it did, but it currently can't. But in any case, the question here is, do we have one or do we have two planets in our own solar system that could support life? Now, we can at least assume one, so that's a fairly safe assumption. Two might be more on the generous side, but for most accepted values, one is a safe assumption here. The next value of L is the number of planets that actually develop life that could potentially develop life. So this is a value between 0 and 1. We don't know how many planets do develop life that could potentially support life. So we know of at least one planet that could support life, and that's our own. In our solar system, if we were to assume that we go based on our solar system alone and we say that Mars and Earth could both potentially support life, but we only see one of those actually doing that, then we would say that this value will be 0.5. Most people assume this is on the low end though, because we just don't really know how many planets that could support life actually do develop life in that case. So a value less than 0.5 might be acceptable here. I don't know. Nobody knows. Just make an assumption here. And this one will obviously affect the outcome of D more than many other ones will, because if you assume low, then D will be low. If you assume high, then D could potentially be high as well. Now, I is the fraction of those planets that will actually support intelligent life. Again, this is not a known value. We don't have any idea about how many planets actually support life, let alone intelligent life. So this is another speculative one here. We know our planet supports intelligent life, but we know of no other planet that actually supports life or even intelligent life. So this could be a low number, 0.001, could be a high number, as high as 1. So again, it's a fractional number, and you know what kind of data type to use for decimals. And the next value is C, and this is the fraction of planets that will develop a detectable signal. So in the event that a planet does develop intelligent life, that intelligent life develops the technology they need to broadcast a signal into space that could be detected by us on Earth. Now, currently, we know of only one civilization that does this, and that's our own. So again, this value is open for debate. It can be very high, it can be very low. I don't know. Nobody knows. So just assume something. Most folks do tend to think that if a civilization is intelligent species and they will eventually get the technology they need to develop broadcasting signals into space. So some people tend to put this one on the high end, but again, it's just pure speculation. No one really knows. And T is the amount of time in years for a given civilization that will actually last long enough to broadcast a signal into space. So is that value 100 years? Currently, we've been doing broadcasts into space since about the 1930s, so we've been doing it around 90 years. And as a species, that's fairly short in the grand scheme of things, even if we have been a technologically advanced civilization for the last 100 years, enough to broadcast into space that is detectable by some remote satellite or some remote kind of telescope that's looking for our kind of broadcast on another planet. We're looking for similar things on Earth using something called SETI. And this is, again, speculative here. It could be 100 years, it could be 1,000 years, it could be 10,000 years. We just don't know before we either get hit by a meteor and our civilization ends, we destroy ourselves. It could be even as long as millions of years. We just don't know how long this number is. So again, incredibly open to values. We could choose one on the low end, one on the high end. And again, this is going to impact the outcome of this equation quite radically. So now that we understand the values and what they represent, let's go and look at my example and my implementation of this in Python, and then you can develop your own and then submit it to me for your challenge. All right, I have my implementation of the Drake equation in Python pulled up here in Tony. I'm got it obfuscated so you just can't copy what I did, but I want you to develop this. And this is kind of what I'm looking for, is something that looks like this. How many new stars in our galaxy form each year? So I'm going to assume 2 based on the observed value in our galaxy. And the number of those stars that actually have planets around them, I'm going to go with the accepted value of around 0.5 here. And the number of planets per star that can support life, I'm going to go with the assumption that at least one can. That is what we know from our own solar system. We have one planet that supports life. The number of planets where life actually develops. And this is where this gets incredibly speculative. I have no idea. And so I'm going to say, let's just say 0.01 for good measure here. Let's say out of 10 planets, only one of those develops life. I don't know what that value could be. It could be higher or lower than that. And intelligent life, let's just say out of those, let's just say only 10 of those develop life. And then how many of those actually develop a detectable signal? I'm going to go with, let's say, a fraction of 1. In that case, I'm going to assume that if they're intelligent, they're going to develop the technology that has the potential to broadcast a signal into space that would be detectable. And then how many years would that civilization last? Currently, we only know of one civilization that has been doing this for about 90 years. Maybe it's longer than that. I don't know. So let's just say 2000. And if I run these numbers, I'm going to get some kind of value that looks like this, where I have 20 civilizations in our galaxy that are currently technologically advanced to broadcast a signal that is detectable into space. Now, out of billions of stars, that's very, very few. So it's like looking for a needle in a haystack. We just don't know. We haven't been able to find any civilizations that are currently broadcasting something that we have been able to detect with our technology. So again, this number might vary wildly depending on what numbers you put in. Of course, you could go longer than 2,000 years. You might say a fraction of planets with stars is actually around 1, or the number of potential planets with life on them is actually somewhere around, maybe if there is a planet that supports life, that it will develop life. So you could maybe make that number higher. I don't know. Depends on what you put in here. This can vary wildly. But again, something to think about. And this makes it also for a fun challenge here. So write me a program that does what mine does here and submit it in the challenge, and I'll put you in a drawing to win a $10 Amazon gift card. So submit those to me, and looking forward to your submissions on Cool Enough to Code. So thanks for watching, and looking forward to seeing you on future lessons. If you like this content, please consider liking this video, then clicking on the subscribe button to subscribe to our channel, then clicking on the bell notification icon and selecting all so that you'll get notifications when new content becomes available on our channel. You can also click on the share icon and share this video to any of your social media platforms. Sharing this helps make it more widely available for those who might be interested in coding. Also, consider following us on Twitter so you can see updates on Twitter whenever new content becomes available, as well as other announcements related to Cool Enough to Code. You can also help us out by becoming a patron on our page by going to our Patreon page at patreon.com/coolenoughToCode and then clicking on Become a Patron. And there you can find out more information about how you can support our work with Cool Enough to Code. And like always, you can check us out online at coolenoughToCode.com. There you can find a schedule of all of the upcoming lessons that we have. You can also find out more information and reach out to us online here. And you can also watch the live stream as it comes out each week on coolenoughToCode.com as well. And like always, thanks for watching this lesson on Cool Enough to Code.